Hi all, this is Ms. DeMeo. I'm going to be going over our 3 spiral reviews that we've had so far. So hopefully this will help you in preparation for the quarterly test. So we're starting with spiral number 1, question 1. We have this table for isotopes here, and the question asks us which numerical setup can be used to calculate the atomic mass of silver. So in this table we see the two we see the 2 different isotopes of silver. An isotope, remember, is the same element because it has the same number of protons, but different mass, different number of neutrons. So we have the actual atomic mass in atomic mass units for each one, and then we also have its natural abundance. So this is like the percent of it that we have in the world. So out of all the silvers in the world, 51.8% of them weigh 106.905. We want to determine the overall. How we would need to do that is we would need to multiply the atomic mass by its natural abundance, but make sure that you divide it by 100 because it is a percent, right? Now, initially looking at and then you would add these two together. You would sum them to get the answer. So looking at these initial ones, we want to make sure that Ag107, that weight is accurately multiplied by its natural abundance. The 2 choices that don't do that are C and D. But what makes B the correct answer? Well, B has the percent value listed. If you don't have the percent value listed, then I think you want to multiply by 51.8, and that would give you the wrong answer. When you put the percent, it's like saying 106.905 times 0.518, right? Taking it out of the percent. That's what you want to be doing. Okay. Number 2, which conclusion was proposed as a result of an experiment during which some alpha particles were deflected while passing through a thin sheet of gold foil? So you should recognize this as the gold foil experiment. And the gold foil experiment proved that the atom had a nucleus. Why? Because alpha particles are positive, and those positive alpha particles, some of them were deflected. So when positive goes towards positive, right, they repel. They do not want to be near each other. They repel. So the alpha particles repelled from the nucleus. So that's how we knew that atoms had a nucleus. It also determined that atoms were mostly empty space. Question 3, this is one of the part 2 questions. Compounds that contain the element boron, such as boric acid, sodium borate, produce a green flame when a sample of these compounds is placed in a laboratory burner flame. If this flame is viewed through a spectroscope, a bright line spectrum is seen. State in terms of electron shells why the electron configuration is an excited state electron configuration of a boron atom. So I'm given an electron configuration. They want me to explain why this configuration is an excited state of boron. And they want me to state that in terms of electron shells. So there's 3 electron shells currently. Let's go look at the periodic table. Okay, so we're kind of on our side here, but if I find boron's electron configuration is 2-3. Okay. So boron in the ground state is 2-3. How does this electron configuration compare to that? Well, there's an extra electron shell, right? The number of numbers in the electron configuration tells me there's an extra electron shell. So the correct answer should be that a second shell electron has moved up to the third shell. And even though this is an excited state electron configuration, the excited state electron configuration always adds up to the same number of protons. 2 plus 2 plus 1 is 5, and 2 plus 3 is 5, right? That's how I know that it's boron. Boron's atomic number is 5. So that's explaining why in terms of electron shells. When something is excited, remember that electrons jump up when they're excited, and then when they fall back down, that's when they release the light. That's when we see the light, or the color, or the green flame in this example. Okay, question 4 is asking us about radioactive isotopes. So isotopes, you should know that word. It says to determine the number of neutrons in an atom of Am-241. We have Am-241 in the table. It's used in smoke detectors. In this particular question, that information isn't important to us. We just want to know the number of neutrons. To know and understand this question, you need to understand that this is the symbol of a certain element, and this second number is not the atomic number, it's the mass. I want to know neutrons. Now, I know that mass is equal to protons plus neutrons, so I can find the neutrons from this. And where do I get the number of protons from? I get that from the symbol. The symbol will tell me the atomic number if I go look on my reference table. So first thing is I have to find element Am. It's actually one of the ones on the bottom here. Americium, named after America. It has an atomic number of 95. And I'm not using this number here. I'm going to use the one from the question, 241. 241 minus, what did we say it was? 75? I forgot already now. 75? No, 95. Good thing we checked. (241 minus 95 gives me 146. That's how many neutrons I have. 5 elements with the atomic numbers 112 and 114 have been produced, and their IUPAC names are pending approval. However, an element that would be put between these two elements, well, what element would that be? That would be 113. On the periodic table has not yet been produced. If produced, this element would be identified by the symbol UUT until an IUPAC name is approved. Determine the charge of a UUT nucleus. So I want to know the charge of a UUT nucleus. I need to go to my periodic table for help with this. I know that the atomic number is 113 because it said it's between 112 and 114. So go into my reference table, find 113. It's right here. Hey, look, it matches UUT, like I said it would in the question. And it wants the charge of the nucleus. So if it said just the plain old charge, you would use oxidation numbers, right? This number in the top corner. But because it wants the charge of the nucleus, the charge in the nucleus, well, what's in the nucleus? Inside the nucleus is protons that are positive and the neutrons that are neutral, right? So the only thing that's charged in the nucleus is the protons. So I'm really just looking for the number of protons. The charge of a UUT nucleus is positive because protons are positive, 113. Okay. On to spiral review number 2. This was on the periodic table unit. As the elements in period 2 of the periodic table are considered in order from left to right, which property generally decreases? So I'm trying to look for a property that decreases left to right across period 2. So I have to find period 2 in my reference table, look left to right, and see what decreases. So I have these terms, right? If I don't know what they mean, table S lists them out for me. It'd be really helpful if I could know how to rotate this. Okay, we're gonna have to deal with it on the side. All right, so period 2 is right here, starting with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. I'm going to that section on table S, that's atomic numbers 3 through 10. So I'm looking at this stretch here, 3 through 10. Okay, so what do I notice about these? Well, the first choice is atomic radius. So I'm going to look at the atomic radius for 3 through 10. What's happening to the atomic radius? Hey, look, it's decreasing pretty consistently. So that could be the right answer, but let's just keep going. Number 2, choice 2 is electronegativity. I want to see that decreasing from 3 to 10. From 3 to 10, it looks like electronegativity is actually increasing. Ionization energy is on here. Same thing as first ionization energy, right? Looks like that is also increasing, so not that. And nuclear charge, that is charge of the nucleus, that's increasing. 3, 4, 5, 6, 7, 8, 9, 10. That was like the last problem we just did. So nuclear charge increased, electronegativity increased, ionization energy increased, but atomic radius decreases. And the reasoning behind that, the explanation for this one, is because as you move across period 2, the number of protons increases. And if the number of protons increases, then, right, think about the center of our atom being positively charged. We have the same number of shells because it's in the same period, but the more protons that we have, the more those protons pull on the negative electrons, making the radius smaller and smaller and smaller. 2, which list includes elements with the most similar chemical properties. The most similar chemical properties, that should be a huge signal to you, valence electrons. Valence electrons determine chemical properties. So if I look at where these ones are, I want to see that these elements are in the same group. The same group means the same number of valence electrons. So looking at my reference table, we'll start with bromine, gallium, and mercury. Bromine's over here in group 17, gallium is in 13, mercury is in 12, so not in the same group. It's not 1. Choice 2, chromium is over here. Group 6, lead, Pb, group 14, okay, not the same group. Forget about it, right? Choice 3, oxygen, S and Se. Those are all in the same group. That's got to be the right answer. N, O, and F, those are in the same period. It's not the same period that has the same properties as the same group because it's the same number of valence electrons. Oxygen, sulfur, and selenium all have 6 valence electrons. So it's choice 3. Compared to the atoms of nonmetals in period 3, the atoms of metals in period 3 have what? So you should know that periods have indicate the number of electron shells. So the electron shells we can eliminate because we're talking about period 3. It definitely has to do with valence electrons. Let's just take a look at period 3, comparing metals and nonmetals. You need to remember that metals are over here on the left side and nonmetals are above the staircase on the right side. So period 3, we're looking at valence electrons. Sodium has 1, magnesium has 2, aluminum has 3, silicon is a metalloid, it has 4, phosphorus 5, sulfur 6, chlorine 7, argon 18. So it seems that the nonmetals have more valence electrons than the metals do. And because of that, that means that the non-metals in period 3 compared to the metals in period 3 have fewer valence electrons. Metals have fewer valence electrons than non-metals do. Which element exhibits both metallic and non-metallic properties? That would be a metalloid. You have to just memorize our metalloid elements. It's the ones that are touching the staircase besides aluminum, right? So it's boron, silicon. I'll zoom in on them. Boron, silicon, arsenic, tellurium, germanium, Ge, and Sb, antimony. 1, 2, 3, 4, 5, 6. 6 of them you need to know. So we only have those choices. So looking at what we got, the only one that fits as a metalloid is 4, tellurium. The valence electron of which atom in the ground state has the greatest amount of energy? This is a harder question. So remember, we're going back to this picture. If this little dot is our nucleus and these are our electron shells, the nucleus is pulling all the electrons in. Electrons that are in a higher shell have more energy because they're further away from the nucleus. They need more energy to be escaping that pull to the nucleus, right? The electrons that are down here, low energy because they're feeling the effects of the nucleus more. So which atom in the ground state has the greatest amount of energy? It's going to be the one with the most electron shells. So if I look at my reference table, all of these elements are in the same group: lithium, sodium, rubidium, and cesium. Which one has the most electron shells? It's cesium down here, right? We can see that by the electron configuration. So cesium has the most shells. 6, based on table S, which of the following, an atom of which element has the strongest attraction for electrons in a chemical bond? You should know this term as electronegativity. When I see a question like this based on whatever table, it's a freebie question. Go to that table and compare. We're looking for the element with the highest electronegativity. So I look up a table S, I try to find that. Don't fall for the trap, right? I know we always know that fluorine is the most electronegative, so whatever's closest to fluorine is the highest, but we actually have both chlorine and oxygen as a choice. So we should look them up on table S. If you look up oxygen, it has an electronegativity of 3.4, and if we look up chlorine, it has one of 3.2. So oxygen actually has the greater electronegativity than chlorine. At STP, which element is solid, brittle, and a poor conductor of electricity? Those are traits of a non-metal. Metals have luster, they're not brittle, they're strong, malleable. The only choice that is a non-metal is for sulfur. Which list of elements contain a metal, a metalloid, a non-metal, and a noble gas? I need all 4 of these in my list. So this just takes a lot of work and remembering each thing. Metals, let's define them. They're to the left of staircase, besides hydrogen. Metalloid is those 6 that we just named: boron, silicon, germanium, arsenic, As, and I'm forgetting other ones. I just need to look at the reference table. Boron, silicon, germanium, arsenic, tellurium, and antimony, Sb. So one of these has to be in my second point in my list. A non-metal, the right side of the staircase, and a noble gas is group 18. So I need a choice with all of that. The first choice is going to be a metal. I can eliminate choice 2 because of that. Carbon is not a metal. The second element needs to be a metalloid. So it looks like out of 3 and 4, 1 can only be my answer, right? Because beryllium is a metal, silicon is a metalloid. The other choices do not have a metalloid. Okay. An atom in the ground state contains a total of 5 electrons, 5 protons, and 5 neutrons. 5 electrons, 5 protons, and 5 neutrons. Which Lewis electron dot diagram represents this atom? Well, first of all, what element is this? We know that the number of protons is equal to the number of electrons, and I can know what element this is because the number of protons is the atomic number. So if I look at my reference table, which element has 5 protons? That's boron. It wanted to know the Lewis electron dot diagram. Lewis electron dots show the valence electrons. How many valence electrons does boron have? It has 3. I want the Lewis dot diagram that shows 3 valence electrons. That would be choice 3. The number of valence electrons in each atom of an element affects the element's chemical properties. We have already explained this one. Valence electrons dictates chemical properties and how the atom will bond. Here we have a Bohr model. So here's the diagram below of a specific element. The nucleus of the element contains 4 protons and 5 neutrons. We have a picture. State the number of electrons in each shell of this atom in the ground state. So first of all, we have to figure out what element this is. So it says at the top, though, that it has 4 protons and 5 neutrons. So I definitely know what element it is. It must be, look at my reference table, 4 protons. It has to be beryllium, Be. That's my element. I don't care about the number of neutrons, right? I just care about the protons. State the number of electrons in each shell of this atom in the ground state. So we can use the electron configuration for that. The electron configuration of beryllium is 2-2. So there's 2 electrons in the ground state, 2 electrons in the first shell, 2 electrons in second shell. That's it. Number of electrons in the first shell, that would be, oh, I just wrote it in the wrong spot. So that would be 2 for this one and 2 for this one. Right? Okay. 12 group 1 elements below hydrogen are called alkali metals. Then the first 5 of group 17 are called halogens. Compare the electrical conductivity of alkali metals with the electrical conductivity of the halogen at STP. So you should know that conductivity is only a trait of metals. So metals can conduct electricity, non-metals cannot. So comparing them, metals conduct electricity better than non-metals or halogens. I guess halogens they wanted, right? Halogens. Metals conduct electricity better than a halogen. 13, there are 6 elements in group 14. One of these elements has a symbol UUQ, which is a temporary symbol. It's known as fluorvium. State the expected number of valence electrons for an atom of this element in the ground state. Well, it's in group 14 of the periodic table. What do I notice about group 14 of the periodic table? Check out the electron configuration. 4, 4, 4, 4, 4. 4 valence electrons for all of them. So UUQ also has to have 4 valence electrons. State in terms of electron shells why each successive element in group 14 has a larger atomic radius, considered in order of increasing atomic number. So make sure that you explain as the question says to do. So it says explain in terms of electron shells. Looking back at group 14, as we go down, each time we add an electron shell as we go down the group, right? So, and also this is the way the atomic number is increasing, 6, 14, 32, 50. So I'm following it. So why is the atomic radius increasing in terms of electron shells? The atomic radius increases down a group because each successive has one electron shell, has one more electron shell. Right, so carbon, if I just draw a mini model, carbon has 2 shells, silicon has 3 shells, just to think about it. This is carbon, right? It just keeps getting bigger and bigger and bigger. That's how it will go. All right. Next question. The periodic table of elements has changed over the past 150 years. During this time, many new elements have been added. Their official names have been approved. Blah, blah, blah. I think I'm going to be more interested in this table here, where I'm given the element names, the atomic number, the prior symbol, and their new symbol. Explain in terms of valence electrons. Again, so here we go, explaining in terms of whatever. Why the elements of nihonium and Tennessee would be expected to differ in their chemical properties. Looking at my chart here. Right, I don't know the names of these elements. They're not on table S. They only can be looked at from this picture. But I know that this has the symbol 113 and this has the symbol 117. So explain in terms of valence electrons why they would be expected to differ in chemical properties. So you should know that same number of valence electrons, same number of chemical properties. Let's check out where these elements are based on knowing their atomic numbers, 113 and 117. 113 is this UUT, 117 is UUS. As we can see, they're not in the same group, right? So they don't have the same number of valence electrons. So since NH is group 13 and TS is group 17, their atoms do not have the same valence electrons. And because they don't have the same number of valence electrons, right, I explained in terms of valence electrons, I'm going to say because they have a different number of valence electrons, they would differ in their chemical properties. Do not have the same number of valence electrons. They would then differ in their chemical properties. Okay. All right, last spiral review number 3. Which equation represents energy being absorbed as a bond is broken. All right, so for this equation, your explanation, BARF, right? What does BARF stand for? It's a mnemonic device we use. Broken, absorbed, released, formed. So this equation is representing energy being absorbed as a bond is broken, BARF, broken, absorbed, released, formed. I'm looking for a bond being broken. The only choices that show me a bond being broken are 3 and 4. And which one shows energy being absorbed? That's where energy is on the reactant side, right? Energy is being absorbed, it's a reactant, it's being added. Which characteristic is a property of molecular substances? This one is kind of difficult. Molecular substances, remember, is another name for covalent. Covalent is 2 nonmetals are together. 2 nonmetals, you should remember back to that lab that we did that covalent substances did not conduct electricity in solution, right? They had very low melting points and boiling points. They are not very strong. It's stuff like water, like the gas CO2 in the air around us, that's covalent or molecular, versus like something like salt, right? Like when you put salt in a frying pan, it takes a really lot of heat to melt it. So which characteristics of property of molecular substances? Well, they are really not good conductors. They cannot conduct electricity. That's something that metals or aqueous ionic stuff can do. Low melting point versus high melting point. They have low melting points. High melting point is something that is stronger. The forces between the covalent substances are weaker. All right. Krypton atoms in the ground state tend to not bond with other atoms because you should recognize krypton as a group 18 element. It's a noble gas. Why do they tend to not bond with other atoms? Their outermost electron shell contains 8 valence electrons. So noble gases do not bond. That's why they're the noble gases, right? They're noble. They don't like anybody. They don't bond. The degree of polarity in the bond between a hydrogen and oxygen atom in a molecule of water can be assessed using the difference in polarity. How do we determine polarity? Well, first of all, we use electronegativity to determine type of bonding, and it also helps you determine the polarity, right? Which element in the compound has a stronger pull for electrons, which is going to make it unbalanced, which is what being polar is. The correct answer here is electronegativity. Which element reacts with oxygen to form ionic bonds? Ionic is a metal and a nonmetal. Oxygen we know is a nonmetal, so I'm looking for the choice that has a metal. The only choice that lists a metal is choice 1. Question 6, which formula contains a polyatomic ion? Polyatomic ion, your mind should go straight to table E. A polyatomic ion, poly means multiple, atomic means atom. Multiple atoms. That's what polyatomic means. What does ion mean? It means charge. So a polyatomic ion is multiple atoms with a charge. Table E shows me polyatomic ions. So I'm looking for the compound that has a polyatomic ion. Well, first of all, most of my polyatomic ions have 2 elements. So my compound is going to have 3 elements. I can see that here cyanide Cn minus is polyatomic ion, and I have one choice that is KCN. That must be it. There's no other polyatomic ions here. These are just plain old compounds. Which is the number of electrons shared between the 2 atoms in an oxygen molecule, O2. This comes with drawing Lewis dot diagrams, but for a compound, a Lewis structure. So you start by counting the number of valence electrons you have, because remember, in bonding, only valence electrons are allowed. So oxygen, I believe, has 6 valence electrons. Let's double check. Looking at the electron configuration of oxygen, it has 6 valence electrons, yes. So I have 2 oxygens, and they each have 6 valence electrons. So I have 12 electrons to work with in total. Then I draw my bare bones, I draw my 2 oxygens, and the first thing I'm going to do is connect them with a single bond. I'm actually going to move this over. So I've just used 2 electrons by drawing that bond. So now I have 10 electrons left to go. The next step is to distribute these electrons around the oxygens. Now we're trying to get everybody to 8. So far, this one oxygen on the left only has 2. I wanted to have 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, I just used 8 of my electrons, and I have 2 more here. So looking at this picture, right, the oxygen on the left has 8, it's happy, but the one on the right only has 4. So I need to fix that. So what I can do is I can move around these electrons. So if I move these 2 over here and put them over here, right, I still know that I used my 10, but does both oxygens have 8? Let's count. I'm going to use my little laser pointer if this works. Okay, so 1, 2, 3, 4, 5, 6 for that oxygen. And this oxygen on the right side, 1, 2, 3, 4, 5, 6. So no, they do not have 8 yet, right? They only have 6. So what I can do is I can actually take an electron from here and this electron here, and I can put them together to make a new bond. If I do that, and then I erase these, now let's count again. Hold on, I think I screwed something up. Let's see. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh yeah, I'm definitely missing an electron. Let's just restart. It's fine, mistakes happen. Okay, I'm starting from the top. I'm going to erase this. Okay, so we had 12 electrons to start. That's still true. Draw my 2 oxygens, connect them with a bond. That's using 2 electrons. I have 10 electrons to go. I'm going to distribute them and count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That looks more like it. And I just want to count again. I'll count to make sure I actually have 12. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12. Yes, I do have 12. Okay. But this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That one's happy. This one only has 1, 2, 3, 4, 5, 6. So issues, right? So what I'm going to do is I am going to erase these 2 and just turn them into a bond. When I do that now, let's count again. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. 1, 2, 3, 4, 5, 6, 7, 8. So the oxygens are all happy. Now, what is the number of electrons that are shared? Remember, these lines represent a shared pair of electrons, so each line is 2 electrons. So there are 4 electrons shared between them. That question's a lot of work for just a little bit, right? A solid sample of copper is an excellent conductor. Which type of chemical bonds are in the sample? So it's only copper. It's not copper with anything else. It's just plain old copper. If it's just a metal, then it's metallic bonding. Number 9, which phrase describes the molecular polarity and charge distribution of an HCl molecule? So we can actually draw the HCl molecule if we want. We can draw a Lewis dot. It's good to practice with it, right? So we have H and Cl. I have one H and one Cl. H has 1 valence electron. Chlorine has 7. You can check me on your reference table. So altogether I have 8 electrons to use. First thing I'm doing is I'm connecting them with a bond. When I do that, I actually use 2 electrons by doing that, right? So I have 6 electrons left over. Hydrogen is actually happy with 2, right? These 2 that it has sharing with chlorine are the only 2 it needs. That's how hydrogen is happy. And there's 6 electrons left to go around. 1, 2, 3, 4, 5, 6. Now if I look, chlorine has 1, 2, 3, 4, 5, 6, 7, 8. It has all of its valence electrons that it needs. So what describes the polarity and the charge distribution? Remember, molecular polarity is done by SNAP. It stands for symmetrical nonpolar, asymmetrical polar. So to test this, you can do something called the mirror test. Does it look the same here to here? It looks the same, yes. But here to here, if this was a mirror image, no, that's not a mirror image, right? So it doesn't pass the mirror test. It's asymmetrical, so it must be polar. We can eliminate choices 1 and 2. And it's asymmetrical. That's what polar means. Asymmetrical charge distribution, right? All the electrons are hanging out here by chlorine. Given the Lewis electron dot diagram, which electrons are represented by all of the dots. So just like we've done in the past 2 questions, or 7 and 9, right? You count the number of valence electrons. It's the valence electrons from every element involved. I can double check that. Carbon has 4 valence electrons, and each hydrogen brings 1. Question 11 with a table here. Which statement classifies the 2 compounds? So let's take a look at their melting points. So melting point of compound 1 is high. Comparatively, this one is very low. Boiling point, same thing. Compound 2 is a low one. Compound 1 is very high. Electrical conductivity. This can conduct well as a liquid or an aqueous solution. It does not say solid, notice that. So aqueous solution, you should think back to electrolyte. An electrolyte solution can conduct electricity. An electrolyte is an ionic compound. And this makes sense because ionic compounds have very high melting points and boiling points. That same example I used with the salt. Trying to heat up table salt on your stove, it's not going to melt. So compound 1 must be ionic. Compound 2 is very different. It can't conduct electricity as a liquid or in solution, right? So remember when we put the sugar into the water, that didn't conduct electricity. So, oops, I switched it. It should be 3. Compound 1 is ionic and compound 2 is molecular. Same thing as covalence. Which terms identify the 2 major categories of compounds? This one is very straightforward. Ionic and molecular. Same thing as covalent. Remember that. Given the electron dot diagram, the electrons in the bond between the hydrogen and fluorine are more strongly attracted to the atom of, well, you can use your knowledge of electronegativities for this one, Or you can also just look at the Lewis dot diagram. All the electrons are over by fluorine, right? Fluorine is hoarding those electrons. It's pulling all those electrons towards it. So fluorine, that has the higher electronegativity, is the correct answer there. Given the formula for hydrazine, how many pairs of electrons are shared between the two nitrogen atoms? Now, this question is difficult because it says pairs. It does not say how many electrons. If it said how many electrons, the answer would be 2. But it's asking for the pairs of electrons shared between the nitrogen atoms. There's only one. A line is a pair of electron. Which bond is the least polar? This one. How do you determine polarity? It's the electronegativity difference. You need to use table S for this one. It's always the larger electronegativity minus the smaller one. So whatever has the larger electronegativity minus the smaller one, you're going to calculate a numerical value. So we'll do that. So AS and Cl arsenic is 33, chlorine is 17. 33 has an electronegativity of 2.2, and Cl has an electronegativity of 3.2, so they have a difference of 1.0. Phosphorus and chlorine. Chlorine we said was 3.2, phosphorus is 2.2, okay, same difference, 1.0. Bi and Cl. Bi is 83. Next page. Bi has an electronegativity of 1.9, okay, low, and Cl was 3.2, right? So 3.2 minus 1.9 is, I'm just making sure, 1.3. So that has an even larger difference. So hopefully NCl is smaller. If I look up nitrogen's electronegativity, it has one of 3.0. So 3.2 minus 3.0 is 0.2. The least polar is going to be the closest electronegativity difference. So it will be 4. So hopefully this video helped you with any concerns you have on these first 3 units. Let me know if you have any questions. All right, bye.